Welcome back, students. Now let us talk about an optional topic. We're going to talk about Riemann integrability, and then we're going to talk about some weird example. Basically, we are talking about the last two subsections here. Let's have a bit of a recap. We started with the concept of partition like this. x0, which is equal to a, x1, x2, x3, increase, and then xn, which is equal to b. That was the partition. Visualize kind of like this. Each delta xi is the width of each subinterval, and delta x is the maximum width. If a partition is finer than the other, that means the partition includes all the points of the previous partition. Riemann sum we define like this. For given partition, we have all those width, yes, but height we can select arbitrarily anywhere between the minimum and the maximum. Visualize kind of like this. Same partition, so x coordinates do not change, but y coordinate will change as we run again because yi star is selected arbitrarily. Those are Riemann sums, and then if the limit exists as delta x going down to 0, the common value is called that definite integral or Riemann integral. The question we are going to answer is, when do we have this limit? Let's go back to this. And for that, let's consider the worst possible situations. You see, all those randomness we put in here, yi's are random, and then partitions are random, all those randomness we put in made really diverse quantity, but then again, among them, two Riemann sums really stand out as the worst possible Riemann sums in opposite end of the spectrum. All the yi's here can be overestimated by replacing all these by maximum. And likewise, instead of all the yi's here, we take the minimums of everything. And then what do you get? This is going to be underestimation, and this is going to be overestimation of each individual rectangles. Add them all together, what do you get? Underestimation of everything, overestimation of everything, which we call lower Riemann sum and upper Riemann sum respectively. We use this lower bar and upper bar to represent them. And here is the visualization. Arbitrary Riemann sum is truly arbitrary, so if I run it again, I'm going to get drastically different picture. And here's a visualization of a lower Riemann sum. We have arbitrary partition, yeah, but at each partition we are selecting minimum value. Minimum, the lowest possible values for each partition. Running again, I'm going to get different partition, but still I'm going to get minimum values at each. We get lower Riemann sum. This, by the way, is an upper Riemann sum. At each rectangle, at each interval, we select the highest point, the maximum value. So intervals change, but each time we get maximum values. So this is an overestimation of the real signed area. This one is an underestimation. Consequently, we're going to get something like this. If you overestimate, bigger, underestimate, smaller, so any Riemann sum will be bigger than lower Riemann sum and less than upper Riemann sum. Also, we have another property here. If I take finer partition, so putting my more points in, lower Riemann sums increase and upper Riemann sums decrease. You see, Pi we have say 5 points, Qi we have put more points and we have 15 points. So we took more finer subdivision. In that case, lower Riemann sums increase, upper Riemann sums decrease. And eventually, do they merge at the same point is the problem. Here's a visualization of lower Riemann sums increasing. We have this partition, okay? And then we put several more green points in there so that we made a finer partition. And then let's see, look at this interval here, over here. Here's the minimum of all those. And then because we put several more points, we have minimum of the smaller region, minimum of those smaller region got a little bit higher. And similar thing going on over here as well. So lower sum increased a little bit. How about upper Riemann sums? They'll decrease. Not very good picture. Let's run it again. Okay. Here we have some intervals, and then we took maximum, 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 and then we put several more points in between, the red points. Consequently, if we take maximum of smaller region, we'll decrease a little bit, decrease a little bit. So you see, upon taking finer partition, upper sums decreased, lower sums increased. So the idea is upper sums increase, lower sums increase, upper sums decrease. Are they going to merge? Are they going to merge at the same point? If they do, then that is going to capture all the Riemann sums and then squeeze into the same value. Kind of like squeeze law. So what do? Consider only lower Riemann sums and take the limit. Because this is an increasing limit, always you have to have a limit. The same thing goes to upper Riemann sum. Upper Riemann sums decrease, so the limit always exists. You see, the limit, the sequence is not allowed to go back up, go down, and then it cannot go all the way down to negative infinity because nothing can, because the upper Riemann sums are greater than lower Riemann sums, so they have to stop somewhere. Same thing goes to lower Riemann sums. They have to increase, and they're not allowed to come back down, increase, increase, increase. But it cannot go all the way up to positive infinity because lower Riemann sums cannot reach upper Riemann sums. They are, after all, underestimations, so they have to stop somewhere. And where do they stop? And those are called lower Riemann integral and upper Riemann integral. And by the same logic, lower Riemann integral is always less than or equal to upper Riemann integral. When they're the same, then we say the integral exists and the common value is Riemann integral. When do they have the same value? When you have continuous function, yeah, they're going to have the same value. In some other cases, however, you can still have some Riemann integrability. And let's consider an example that is really, really weird. And okay, here we go. Let's define phi of x as 0 when x is irrational. 1 over n if x is a rational number, which is m over n in the lowest term. Here's a visualization. Oops. We have these points, and then for relatively small denominators, we have those red dots, but overwhelming the majority of the points have really large numerator and really large denominator. And we are pretty much knocking off all the numerator, so the function value becomes 1 over n, gets pretty low here. So we have really large concentration down below. And of course, all the irrational numbers go down to 0. And we have relatively small number of large numbers here. Those are represented in red here. And overwhelming majority go down to this greenish blue band here. They are black. How many discontinuities are there here? It turns out that, it is a little bit difficult to prove, but it turns out that this function is discontinuous at every rational number, continuous at every irrational number. And that's something you can do in analysis. Now let me show you upper Riemann sums, because lower Riemann sum is always 0 all the way. You see, the minimum is always 0, so lower Riemann sum is pointless, they're all 0. Upper Riemann sums, they look kind of like this. You see, you have the maximum value here, maximum at those red points, that's with relatively small denominator, and they correspond to relatively tall but thin rectangles. And then overwhelming majority, the numerous ones, those have very short height. And then what are you going to do? Overestimate the areas of those blue rectangle with this blue bar down here, you see, and then this height we're going to take into limit going down to 0 and go down to 0. And how about the red? They're going to become so thin, they too are going to go down to 0. Consequently, upper Riemann sum converge to 0, and consequently we get Riemann integral as 0. How do we actually do that? That goes a bit too much further up, so I'm not going to do that in calculus course. But I do feel pretty good showing you these pictures associated to this function. Graph of the function, and then the picture of Riemann sums.